Hello, everyone. In this section, we kind of culminate actually the chapter of systems of equations with the topic that we are really working toward. The topic that we're discussing in this lesson is on what's called linear programming, which is a huge, huge item. You can take whole classes on this in college on linear programming. Its applications are extensive. It's used in a variety of different fields. You'll see a few examples today. You'll see actually a historical context of when linear programming was used. So for this lesson, we're going to start by working through one quite large application question. These are kind of big questions. These are not questions that you just think of when you think of like normal math questions when you can just kind of rip them off in 30 seconds or a minute. This actually takes some setting up and some thinking, and there's quite a few steps into the process. So the reason why is because linear programming is one of the most common applications of mathematics in use today. So the context that we're going to use for our first example is going to be found in our current edition of the college algebra textbook. If you have a copy nearby, then you can open your book to page 575. If you don't, I'm going to read the example in the coming slide. But to follow along in class, pause the video until everyone has their book out and open to page 575, as we are going to read the introduction to this lesson as it sets the stage for our context. Those of you who took U.S. history last year and other years, or maybe even this year, you will recall what the historical context that we're going to be looking at. And for those of you taking it now, you're going to be learning about it in spring. So here we go. The page that you'll find in the book looks like this. It has a picture of children watching an airplane fly over, and this has to deal with what was known as the Berlin airlift after World War II. So the Berlin airlift, which ran from 1948 to 1949, was an operation by the United States and Great Britain in response to military action by the former Soviet Union. Soviet troops closed all roads and rail lines between West Germany and Berlin, cutting off supply routes to the city. The Allies used a mathematical technique developed during World War II, which we're looking at, linear programming, to maximize the amount of supplies transported. During the 15-month airlift, nearly 280,000 flights provided basic necessities to blockaded Berlin, saving one of the world's greatest cities. In this section, we will look at an important application of linear inequalities as it gave rise to what is known as linear programming, a method for solving problems in which a particular quantity must be maximized or minimized, and it is limited by other factors. Linear programming is one of the most widely used tools in management science. It helps businesses allocate resources to manufacture products in a way that will maximize profit. Linear programming accounts for more than 50% and perhaps as much as 90% of all computing time used for management decisions in business. The Allies used linear programming to save Berlin. So they've kind of shrunken the linear programming that they did down in the World War II example to one that we can kind of use as a simple example to get started. So the context that they were working with had a lot more factors than what we will work with, but they've kind of simplified the process so we can see an example. So here we go. To start, you need to define what's called the objective function. It's called the objective function because the objective, or the goal, is to make this function output a value that is as large or as small as possible. It depends on the context. If it's like a disease, you would want to minimize it. If it's getting as many resources in, then you're going to want to maximize it. So the objective function is an algebraic expression in two or more variables describing a quantity that must be maximized or minimized. On June 24, 1948, the former Soviet Union blocked all land and water routes through East Germany to Berlin. A gigantic airlift was organized using American and British planes to bring food, clothing, and other supplies to a few million people in West Berlin. Here's the example that they've developed for us to practice and begin to see how linear programming works. The cargo capacity was 3,000 cubic feet for American plane and 20,000 cubic feet for British planes. To break the Soviet blockade, the Western Allies had to maximize cargo capacity. Write the objective function that models the cargo capacity for the Allies if, and then we need to define our two variables. So the two variables that we're keeping track of is going to be X has to be the number of American planes and Y would need to be the number of British planes. Then the objective function is going to be the following. The objective function is always defined by the letter Z. So we'd say the objective function is equal to 30,000, which is 30,000 cubic feet for every American plane, plus 20,000 feet for every British plane. And our goal is to make this as large as possible. Obviously, you would just pick the biggest X and the biggest Y values that you can get. But as we're going to see, there are certain constraints that are going to affect which ones that we can choose. So here we go. Next variables. Good. And now we're going to do the constraints. So as they try to maximize the cargo capacity, they were subject to the following constraints. No more than 44 planes could be used. The larger American planes required 12 people to operate them, while the British planes only required 8 people. The total number of personnel available could not exceed 512, so they only had 512 people that they could use. The cost of an American flight was $9,000 and the cost of a British flight was $5,000. The weekly budget could not exceed $300,000. Recall in the last part that we defined the following variables. Now our job is going to be to translate the following constraints. So it looks like we have 3 constraints that we have to write. So here we go. This is why you define your variables to start. X is the number of American planes, Y is the number of British planes. The very first constraint that they said was no more than 44 planes could be used. That means the number of American planes plus the number of British planes has to be less than or equal to 44. Second constraint. The larger American planes required 12 people to operate. Sorry, not 12, 16. The British, 8, and we only had 512 people. So it had to be less than or equal to 6. So 16 people for every American plane plus, they say 8 people for every British plane. And we had at most 512 people that could be used. Now is the cost. American planes or flights were $9,000 for every American plane flight, plus $5,000 for every British flight, and our budget had to be less than or equal to $300,000. So there's our 3 constraints. We're going to need to graph those then and find all the points that would make all of these true. So the next part, after you've defined your constraints, which we've done right here, x plus y is less than or equal to 44. Right there. 16x plus 8y is less than or equal to 512. And then the last one, 9,000x plus 5,000y has to be less than or equal to 300,000 shown. There's our constraints. Now we're going to graph them. So to graph them, we're going to use intercepts to do this. You could solve all of them for y if you'd like to, but intercepts are going to be much easier. So for the first one, how do we use intercepts? It's a little table. If I do 0 American planes, because I think X was American planes, is that right? Yep. If I do 0 American planes, then I have to do 44. If I do 0 for Y, it has to be 44 for X. So 44 and 44. These go up by 2, so right there and right there. Then I would use a line and draw those in. So there's the first one. Let's actually make it green so it'll be easier to track. Okay, so there's the first constraint. Second one. If I, again, do 0 American, so 0, I can only use British, and British took 8 people, and I had 512, so 512 divided by 8 would tell me I could do 64 British. So 64 British would be right there. If I did 0 British and I did only American, well, 512 divided by 16 has to be half as much as we had before, so it has to be 32. So 32 for the American. These are going up by 2s, that's right, yep, right there. So then I need to graph the line that connects those two. So there to there. Looks like that. Last one. Again, finding intercepts, just like a very small table. 0 American, 300,000 divided by 5,000 is going to give me 60 for Y. 60 British. Or if I did 0 British, 300,000 divided by 9,000 American would be 33 and a third. So 32, 33 and a third would be somewhere like in here. And if I graph this, fine, I get something like that. Now, I want the region that is below all of them. So below the red, below the green, below the purple. That region, to me, looks like it would be right in here. So any point in this region would satisfy all of the constraints. So it would make all of the constraints true. Now our goal is to find the point in that region that will also make the objective function as large as possible. Well, you could think about, it could be any point in here. But we already said, noticing going back before, my objective function was this guy. We want to make this as big as possible. So we need to choose the biggest x and the biggest y we can. So think about this. I wouldn't want to pick a point out here because I could pick more y's and more x's. So you keep working your way around. Like I wouldn't want to pick a point right here because I could go higher. I wouldn't want to pick a point right here because I could go higher. You would eventually notice that the only possible points that are going to be the ones would be the ones where it's going to be a corner point, because then you couldn't go any higher for y or any more to the right for x. So the corner points are the only ones that I would want to check in the objective function. Those are the only ones that would make the objective be as big as possible, because they're the only points I can't go any more up or any more to the right. So I need the coordinates for all of these. These ones are fairly simple to get. This bottom one right here, we already said was 32, 0. This one up here, we said was 0, 44. We did that when we graphed them. This one right here, I would use technology to get it. So if you type these equations in Desmos, or you could solve them by setting the equations equal to one another and then solving for x and solving for y like a system of equations as we have in the past. But I'm just going to use technology to help us out. And when I ask Desmos to graph it, there's the graph. There's our corner points we said right there. There's the 32, 0. There's the 0, 44. And I also want that one. It's 20, 24. So the last point would be 20, 24. So the points I need to check are one of those three. I'm going to plug the coordinates for each of those points into the objective function and find which one makes the objective function as large as possible. And then that's going to be the correct combination that I would want to use. So if I check 0, 44, if I put 0 in for x and 44 in for y in the objective function, I'm going to end up getting z equals 0 plus this is 1,320,000 cubic feet. That would be 1,320,000. So there's the first combination. Second, 20 for x, 24, so this would be 20 American, 24 British. This is going to end up being, let me see, 20, 1, 2, 3. I want to make sure I did the last one right because that doesn't look right. 4, 4, that isn't, that's 8, yep, this is incorrect. The 0 was right. I plugged the 44 into the 30. So going back, 0 plus 20,000 times 44, that has to be 880,000. So 880,000 cubic feet would be this one. Second one, 20 times 30, that's going to be 600,000. That one's easy enough to do. Plus then 24 times 20,000, that's going to be 480,000, which would be, when I add those two together, what, 1,080,000 cubic feet? And then the last one, 32 times 3 would be what, 960? And then plus the 0, so 960,000. So the one that gives me as much cargo capacity as possible is going to be this one. So the combination that I should use is 2024. But sometimes it could be one of the endpoints. It might have been the case where it would have been better just to use British or just to use American planes. But in this case, it was better to use a combination. It would be best if we use 20 American, because that's the X coordinate, and 24 British, because it gave us over 1 million cubic feet of carrying capacity. So there you go. That's an example of a historical application of linear programming. I'm going to have you try setting up an objective function and writing the constraint inequalities. So it says bottled water and medical supplies are to be shipped to survivors of an earthquake by plane. Each container of bottled water will serve 10 people and each medical kit will aid 6 people. So we should probably have X is going to equal the bottled water, so number of bottled water. Y is equal to number of medical kits. first thing you should probably do is actually define your variables. Now your task is to write what the objective function is. What are we trying to make as large as possible? And then write the two constraint inequalities. So maybe give you a chance to read it. The ball of water containers are 20 pounds. I should say containers, not. And the med kits weigh 10 pounds. Each plane can carry no more than 80,000 pounds. The bottled water containers and the med kits each take up 1 cubic foot. Each plane can store no more than 6,000 cubic feet. So we have a weight and a space constraint. So pause the video now, try to write the objective function, try to write the constraint inequalities. There's no solving, you're just practicing setting these up. So pause the video now for maybe a minute and a half, try to set up the objective function, so z is equal to, and then try to write your constraint inequalities. So pause the video now, unpause it after a minute and a half, 2 minutes, and everyone's had a chance to try. Okay, welcome back. This is what you should have got. You should have got that the objective function is 10x plus 6y. That's what you want to make as large as possible because it's 10 people for every water container and 6 people for every med kit. The weight capacity is 20 pounds for every water container plus 10 pounds for every med kit. It needs to be no more than 80,000. And the bottled water containers, or the water containers plus the med kits, each take up 1 cubic foot, so 1 for each. Has to be no more than 6,000. So these are your constraints. Then you would graph these constraints, find the corners, and then check each corner's coordinates into the objective function and find which one will make this be as large as possible so you can serve the most amount of people. Okay, we're going to try type of questions they ask about in the book. So in the book, sometimes they have context, sometimes they don't. Sometimes they've already just set up all the stuff for you. They're just asking you to practice the mathematical objective. So here it says to state the maximum and minimum value for the objective function, because it might depend on the scenario, according to the following constraints. So this is the objective function right here. And these are the constraints. So you need to graph the constraints first. So x is greater than 0, y is greater than or equal to 0. These right here just say you're in the first quadrant, which is why the graph I've given you is only in quadrant 1. Now you actually need to graph these ones. So again, you could solve for y, or you could just use intercepts. If you put 0 in for x, then y would have to be 4, because 12 divided by 3 is 4. If you put 0 in for y, 12 divided by 2 would be 6. So there is the first one. Second one is 0 for x, and 3 for y, and then vice versa. So it look like that. Now you'll notice there are 4 corner points right here, because I want the region that is below the purple and above the blue, and that would be anything in between or on those lines. So any point in here would work. I want to find the one that's going to make the objective as big and as small as possible. So I need to check all 4 of these. So there are 4 corner points here. There is the point 0, 4, 0, 3, 3, 0, and 6, 0. So it doesn't matter which order you check. If I want to check 0, 4 and I put it into the objective function, z is equal to 4x plus y, I would end up getting 4 times 0 plus 4, so z would be 4. Then I could check 0, 3. Z then would be 4 times 0 plus 3, so z would be 3. And I could check 3, 0. Put 0 in for y, 3 in for x, so 4 times 3 plus 0, z would be 12. And the last one is 6, 0. Z would equal 4 times 6 plus 0, so z would be 24. And then I go looking for the largest and the smallest. The maximum occurs when z is 24 at the point, or the combination, 6, 0. The minimum is 3 when x is 0 and y is 3. So they will give you situations where they want to know what the biggest and the smallest values actually are. Can I give you a chance to try? This one I've already actually graphed the constraints for you. I want to know if for the objective function z equals 3x plus 2y, what are the maximum and minimum values for that objective function, if this is your constraints. So you need to check all 5 corner points, see which one makes z the biggest, and see which one makes z the smallest, and then say what that value is for z. So pause the video now for maybe 2.5 minutes. Unpause it once everyone's had a chance to try and check with a neighbor and wants to see what the answer is. So pause the video now, please. When you check all 5 points, you'll find the maximum for value for z is 39 at the point 512. The smallest value is when z is equal to 13, and that occurs at the point 3, 2. And that is it. That is how linear programming works. It's a highly involved process. You can imagine when you have a business or a company or a government agency working with this, they have hundreds or thousands of constraints that they're using a computer to constantly be checking the objective function to see which combination is going to be the best, either the smallest or the biggest, depending on the situation. So thank you very much and have a good day.